Welcome to Radonix. In this video, we'll walk you through everything you need to get started. From understanding the interface, controlling the axes, staying safe, to setting zero correctly. Whether you're a new user or just need a refresher, this guide will help you run your machine with confidence. All right, let's introduce you to Radonix. The Radonix interface has a main screen. At the top of the screen, there are several status lights. There are two main panels here, for axis coordinates and for axis speed and related settings. In this section, we control the X, Y, Z, and A axes. The stop button. This is program speed percentage. On the left side, you can see the spindle speed settings for turning, and the lathe cutter is also controlled from here. This section is for running the program, and the other part is for editing the G code. Let's start from the top. When the machine is connected to the laptop and powered on, the status lights turn green. Right now, I'm in simulation mode. When the machine is online and home is executed, the lights turn yellow. Your machine has three main axes, X, Z, and A. The indicator lights for these axes are on. There are also two other lights here, alarm for error detection, emergency for critical situations. When a servo motor has an error, the alarm light turns on. A servo motor is the one that moves the axes and works with feedback. There are three separate motors for the X, Z, and A axes. When one of these motors fails, the axis light turns off. The alarm light turns red. That's how you know the machine is in an alarm state. In the status bar at the bottom of the screen, you'll also see something like Motor Alarm X or Motor Alarm Z, which helps you pinpoint the issue. You can also check the control panel. By checking the alarm number, error code, you'll know what the problem is and how to fix it. Most errors can be resolved using one of these two methods, turning the machine off and back on, pressing the alarm reset button. The emergency light is for critical cases. There are two emergency buttons on the machine. In dangerous situations, press this button to immediately stop the machine. But the best practice is to first press the pause or stop button, either from the program or the controller. If that doesn't work, then press emergency. If that still doesn't help, power off the machine completely using the power button. I always give this example to customers. What is an earthquake drill for? So that if a real earthquake happens, people don't panic and know what to do. It's the same with this machine. You need to be prepared with scenarios in advance. Examples, the wood breaks. The axis was rotating and the wood got stuck in the chuck. Smoke is rising. You know how sometimes when you hit stop, suddenly thick smoke appears? Now imagine even after pressing emergency, the machine keeps running. That means the stop command didn't reach in time or the motor's still engaged. With Radonix, when emergency is activated, the whole system shuts down. If it still doesn't respond and the machine keeps moving, then press pause. If that doesn't help, press emergency. If that still doesn't work, shut down the machine with the power button. These three options should always be in your mind so you don't get confused when something happens. After shutting down the machine, wait for it to calm down. Then, close the Radonix software. If a tool or piece is stuck, manually move the axis back, only when power is off and the axis is de-energized. Important note, when you turn the machine back on, the automatic clutch is engaged. If the cutting tool is still inside the piece, turning the machine on may break the tool. So always, after shutting down, wait a few minutes and make sure nothing is stuck. Once you're sure, turn the machine back on, open the Radonix software, run home, then continue your operation. All right, so here we have two types of coordinates. The first type is called absolute coordinates. If you've worked with CNC machines or are familiar with them, you know that the first thing we need to do after powering the machine on is to home the machine. What does homing mean? It means the axis moves to the end of its path until it hits a limit sensor. That point is then set as the reference or home position. For example, the Z-axis moves until it sees the sensor, and from that point, it can move forward about 35 centimeters. The A-axis, for instance, can rotate about 10,000 times. This process defines a valid motion range for each axis. After homing, all coordinates reset to 0. So, if A shows 360, it's still considered 0 because it's back at its original position. Homing ensures that, for example, the X-axis won't move beyond a certain red line or leave its defined range. Everything inside the red rectangular frame is considered absolute coordinates. But when we're working on a specific workpiece, we use relative coordinates, or workpiece coordinates. Positions defined within the actual material. Take a look at the orange marker. This shows where the workpiece starts. In this case, it says Z equals 335. If I rotate the view, you'll notice it's sitting just a bit above the red reference line. I mentioned earlier that the total Z travel of the machine is about 35 centimeters. This marker is placed just above the original red line, which represents the machine's zero. Now, if we assign a lower Z value, which means moving the tool forward, the number decreases. For example, if Z becomes 300 or 100, it means the 0 point has been moved up. This is your work zero, and it's really useful when setting offsets or running your program. With these coordinates, we can confirm that, for example, X is properly set to 0. The screen also shows the shape or dimensions of the part to be machined. At the top of the screen, you'll also see the file name and file path. The work size section shows the size of the part. dx equals 800 millimeters is width, dy equals 0, dz equals 20 millimeters is height, dA equals 450 is A-axis rotation. It might not be clear in this specific view, but in rotary mode, it's shown more accurately. The total machining length might be shown as 6,400 millimeters. If you're quoting based on length, cost per meter, this tells you how far the machine has moved. You can also change the 3D view using these tools: zoom in, zoom out, view from top, front, left, or perspective. Now let's talk about the axes. Take the x-axis, for example. It has a velocity setting, a travel length, a reference point, and a current value, e.g. x equals 0. The same setup applies to z and a. Speed adjustment example. Let's say the speed of x is set to 80 millimeters per second. That means when you run a command like x+, it moves at 80 millimeters per second. If you increase the speed to 180, it'll move faster. But in general, it's better to start with a lower speed, especially at the beginning when there's a chance the tool might hit something. So I usually set it to 80 because it's safer. Currently, for example, z speed equals 40, a speed equals 10. You can increase or decrease these values based on the situation. When doing zero setting the workpiece origin, the speed should be low to avoid tool collisions. But if you're far from the chuck or piece, you can move faster. Once you're within 2 to 3 centimeters of the piece, slow down again. We have two ways to adjust speed. Change the direct numeric value, e.g. x equals 80 owes x equals 50. Use the percentage slider, which controls the overall program execution speed. Both methods work the same, but the percentage slider is faster to use. Example, if x equals 80 millimeters per second and you set the slider to 10%, that becomes 8 millimeters per second. The same applies to z and a. 8 millimeters per second, 4 millimeters per second, 10 millimeters per second. If I set the slider to 50%, the speed increases. If I put it at 100%, it goes back to the full original speed, 80 millimeters per second for x. In summary, one way to control speed, adjust the number directly. Another, faster way, use the percentage slider. My recommendation, use the slider, since it's faster and safe. In this segment, we're diving into step mode, axis zeroing, and z-axis calibration, essential for precise diameter adjustments and clean cuts. Whether you're just setting up or fine-tuning your tool paths, this walkthrough will help you master precision control using the Radonix system. Let's get started. All right, so here we've got a setting related to step length, how far the axis moves with each step, and it's measured in millimeters. By default, this option is off, but when you hit the step button, it becomes active. You'll see its icon looks like a solid line, and once it's activated, it turns into a dashed line. That means step-by-step movement is now on. For example, let's say I've set the step value to 1. Now if I press the positive button for the x-axis, it'll only move 1 millimeter, no more. If I set it to 10, every click moves the axis 10 millimeters. If I set it to 100, one click moves it 100 millimeters. And if I press stop again while in this mode, it stops immediately. So this step value gives you precise control over how much the axis moves. When do we use it? One good use is during calibration. Like if we tell the axis to move 1 meter, we can check if it actually does move 1 meter. Usually you want to keep this number low. Larger values are rarely used unless you've got a specific reason. For example, when doing precise zeroing, you set it to 1 millimeter so you're sure it's only going to move a tiny bit, no risk of hitting the chuck or the part. So just remember, keep the value low most of the time. If you raised it, don't forget to set it back down afterward. If you leave it high, even a small button press might move the axis a lot, which could crash the tool into the part or damage the machine. Important tip, if you're not using step mode, just switch it back to the solid line icon. That turns it off. Or at the very least, make sure the value is 1 millimeter. That way, no surprises. Now about movement speed. This part's about continuous mode, which means when you hold down an axis button, like X, the axis keeps moving smoothly at the current speed. If you want to switch from continuous to step mode, just click that same icon, solid dashed. Quick breakdown, solid line, continuous movement, dashed line, step-by-step movement, and the step amount is whatever number you've set in the box above. One last example, if your step value is set to 1, every button press moves the axis 1 millimeter. You'll even see it on screen. If your coordinate is 1,157, one click moves it to 1,158, then 1,159, and so on. Same goes for the Z and A axes. They all follow the same step amount you've set. All right, so that step mode button we talked about, it applies only to the axis you're actively controlling. We usually work in step mode, especially when we need to make precise adjustments. For example, let's say I've set the step value to 1 millimeter, but now I want to move less than 1 millimeter, say 0.1 millimeter. No problem. All I have to do is lower the percentage speed from the bottom, where it says 100%, and leave the step value at 10. That way, 10 multiplied by 10% gives me 0.1 millimeters per click. So now, every time I click the axis button, it moves exactly 0.1 millimeter. One important point. When you're in stop mode, the step speed percentage and the continuous speed percentage are independent. For example, I might have the continuous speed set to 80%, but when I switch to step mode, it might be at 50%. Personally, I usually keep both at 100% just to keep things simple. Now let's talk about the third column on the screen. This one shows your current position, basically your reference point. For example, let's say I bring the Z-axis down to -335. Right when the tip of the tool touches the tip of the chuck, I press the Z0 button. That sets this point as the starting position for Z, the Z0. Same goes for any axis. Wherever your tool is, if you hit the 0 button for that axis, that position becomes the new 0. Example, if the A axis is at 90 degrees, pressing a 0 makes that your new rotational 0. If X is at 1300, pressing X0 makes 1300 the starting point for X. And if you want to go back to a specific value, say you know the original position was 205, you just type it in or select it from the options, hit enter, and you're back there. How to decide where to place your 0 based on the workpiece. When you mount the part, think, where do I want the machine to start? From the beginning of the piece, from the center, or maybe 2 centimeters ahead? You can set the X0 anywhere you want. Let's say you know X equals 205 means the tool is exactly aligned with the edge of the part. The chuck, 3-jaw, has a 50 millimeter diameter, and your part is 100 millimeters. So, obviously, the tool can't go lower than the chuck. In this case, X equals 205 is perfect. You're starting right at the edge. But what if your chuck is 50 millimeters, but your workpiece is only 40 millimeters? Now you've got a problem. If the tool moves down too far, it might hit the chuck. So in that case, you should shift the X0 forward, maybe by 10 millimeters. so the tool clears the chuck and doesn't chip or crash. Recap. How to set X0 properly based on the part. Let's say your model is 1 meter, and the wood is also 1 meter. In that case, set X0 right at the start of the wood. X equals 205. But if your model is 42 centimeters and your wood is 50 centimeters, if you start at the very beginning, the tool might go too far and hit the chuck. The solution? Shift the X0 forward a bit. And don't forget about the end of the part either. You don't want the tool crashing into the tailstock or the rear edge of the part. Now, let's talk about Z and how it relates to the thickness of the part. The Z-axis is a bit different than X. Z determines how thick or thin the part turns out. For example, your Z0 might be at minus 335. If your part turns out a bit too thick, like 2 to 5 millimeters over, you need to make it thinner. How? Just increase the Z value slightly. Let's say you add 1 millimeter to Z. The tool will cut 1 millimeter from the hop. And since the part is round, it'll cut 1 millimeter from the other side too. So, overall, the part becomes 2 millimeters thinner. That's how we make symmetric cuts on both sides of a round piece. If you only remove material from one side, the result won't be even or balanced. Let's say you change the Z value from negative 335 to negative 335.5. That means the tool will go half a millimeter deeper. Since it's cutting both sides, you'll actually remove 1 millimeter from the total diameter. So if your part has a bald spot, in other words, an area didn't get cut properly, you don't need to regenerate the whole G-code or remove the tool, just slightly increase the Z depth manually, like from 335 to 335.5 to cut a bit deeper. And if you realize the part has become too thin, no need to go deeper, just bring Z back to its original value. When wood diameters vary, handling it with Z passes. Let's say you have a bunch of wooden parts and some of them are 2 centimeters thicker than the rest. You don't want to generate a new G-code just for those, right? No problem. What you can do, just lower the Z value, for example, from 335 to 325. If each pass removes 5 millimeters, then 2 passes take off 10 millimeters from each side, which means 2 centimeters from the total diameter. After that, just hit reset, bring the Z back to its original value, and continue the program like normal. This way, even thicker parts can be machined without overloading the tool or using a separate file. Or say you have 100 pieces with a 10 centimeter diameter, but 20 of them are 12 centimeters. You've got 2 choices. Create a separate G-code for each size, or just tweak the Z for the thicker ones, so you avoid putting too much stress on the tool. Let's continue with part 3. Now we'll cover calibrating the rotary axis, homing procedures, and G-code optimization for smoother performance with your Radonix system. If you're ready to take control of the next level, let's get started. The A-axis is for rotary motion. It's not used much unless you're doing special jobs. Example, you accidentally mounted the piece at an angle. It should have been vertical, but you don't want to remove and remount it. So what do? Reduce the A-axis speed. Manually rotate it using the controls until it's aligned. Then hit A0. This sets the current angle as the new 0. Say the piece was at 255 degrees. You rotate it to straighten it, then hit A0. Now that angle becomes your base reference. You can even reuse this setting for the next part. But ideally, for better accuracy, physically mount the part straight from the beginning. Don't rely solely on the A-axis 0. What is the W-axis? Your machine technically has 3 axes, X, Y, and Z. But Radonix also shows a virtual axis called W. This W-axis is used for graphic representation of movement. PowerMill usually doesn't generate W values, but sometimes, depending on the post-processor, your G-code might include W. If the W position looks off, you have 2 options. Manually adjust the W0, or use a post-processor that doesn't include W. But honestly, W is super rare, maybe used in 1% of cases, so don't worry too much about it. Stop button and axis movement directions. Your axis movements work like this. X plus moves towards the tailstock. X minus moves toward the chuck. Z minus always comes towards the operator. The positive directions follow a clockwise rotation logic. The stop button always works, no matter what mode you're in. There are 2 stop buttons in the software, one near the program controls and one near the manual jog controls. They both do the same thing. Homing, the fundamental step. Every time you open Radonix, the first thing you should do is home the machine. Why? Because until you home it, the machine doesn't know where it is. The coordinate system is meaningless without homing. You must home in any of these three cases. You closed and reopened Radonix. You turned the machine off and on again. One of the axes gave an alarm and coordinates were lost. Other than that, there's no need to rehome. The homing speed is fixed and slow. You can't change it. There's also a Go to Zero button, which sends the machine to the workpiece's 0 point. But that one's a bit limited. For example, if you click Go to Zero, the machine moves the X, Y, and A axes back to their start positions. But Z stays slightly above the part. It doesn't go down and sit directly on the workpiece. That's intentional, to avoid collisions or damage.
Homing versus go to zero. What's the difference? When you press the home button, the machine axes move toward the corner of the screen, meaning they go to the end of their travel path. But when you use the go to zero command, the machine returns to the work 0 point, not the machine corner. That's an important distinction. Home sets the machine 0, the system's reference point. Go to zero takes you to the work 0, your project's start point. Spindle speed settings and safety tips. Look, we didn't set the lathe rotation speed to 0, because if we did, it could cause errors. Like if you're not paying attention and the speed is too low mid-job, the tool might hit the piece. I set it to a low speed with a maximum of 2900 RPM. But we never really work at 2900, only if the piece is super detailed and you want a very clean finish with a high speed. Up to 2000 is fine, 2100 is the absolute max. Just be careful not to go too high. If you see the speed climbing too much, bring it down. Especially when you're roughing, you can use low speed to check for imbalance or wobble in the piece, like during the first pass. The first pass should be slow to give you room to assess things. You can usually tell from the machine sound whether it's under load or not. If you feel it's under pressure, you can either increase the speed or lower the feed rate. This gives the tool more time to cut through properly before moving to the next point. Also, if the wood is dry and your tool is sharp, you can tell from the shavings. The longer the shavings, the better. Some even say that's an art in itself, the art of machining. Clutch, tool, and rough cutting safety. The lathe button only works when the clutch is off. If the lathe is running and you engage the clutch, the spindle shuts off immediately. Never can turn on both clutch and lathe at the same time. When one turns on, the other automatically shuts off. It's a built-in safety feature. Use the indicator lights to check status. Bright color equals active. Dim color equals inactive. Running the program from a specific line.
This part relates to program execution. For example, starting from line 100, that number shows the G-code line you're working on. You can scroll through the program and preview toolpaths. Yellow equals current tool position, orange equals work 0 point, blue equals selected line to start from. Just double-click any line, hit start, and the machine will begin executing from that line onward.
Pause and reset controls. The pause button temporarily stops the machine. It's the same as the other pause button next to the axis controls, just located elsewhere. When you hit reset, the green highlights on the screen disappear, which means the program is fully reset and ready to start again from the beginning. To activate the start button, a machine must be homed first. So if you open Radonix and notice the start button is disabled, it usually means you haven't done the homing or the machine is in emergency mode. Look at the bottom of the screen. It'll tell you the exact reason, like emergency active or a specific error message. If you're unsure how to fix it, it's best to contact support. 2. Running the program from a specific line. You can scroll through the G-code using page up, page down, or a mouse scroll wheel. When you reach the line you want to start from, double-click on that line to select it, then press start. The machine will run from that point onward. Tip: use the mouse wheel for fine-tuning your line selection. It's smoother and more precise. 3. Important safety tips before starting. If homing isn't working, check these first. Make sure the clutch isn't engaged. Press down, because if the clutch is down, the clutch sensor won't work and the machine won't be able to home. If everything seems fine but it's still not working, close Radonix completely, reopen it after powering on the machine. Very important,
Always turn on the machine first, then open Radonix. If you do it the other way around, opening Radonix first, some commands like spindle activation may be triggered immediately, which could cause the tool to hit the workpiece. Speed settings for repeated jobs, batch work. If you're cutting multiple identical parts, batch production. For the first piece, start with low speed, like 50%. Watch the machine closely to make sure everything's working correctly. If it looks good, for the rest of the parts, you can safely set a higher constant speed, like 70%. You don't need to adjust the speed for every single part, just be careful on the first pass. That's the most important. Adjusting feed rate in the G-code. If you want only the first pass to run at a lower speed, find the line in the G-code where it says something like F1000. Open the Edit G-code section, change F1000 to something lower like F700. That way only that line runs slower and the rest of the program continues at normal speed.
Thanks for watching. If you found this tutorial helpful, don't forget to like, share, and subscribe for more CNC tips and Radonix system walkthroughs. Got questions or want us to cover something specific? Drop a comment below. We'd love to hear from you. See you in the next video.